Thank you for joining us. Please note there will be Q&A after the presentation, so feel free to submit questions during the session. Then join us in the breakout lounge for in-depth conversations with our speakers and to network with other attendees. But before we get to that, I'd like to welcome our next presenter. Philip Keller is responsible for marketing and product management at Metrolab Technology SA. Before joining Metrolab, Philip worked as a senior manager in ASCOM as a researcher in ultrasound medical imaging and for Microsoft, Boeing, and several startup companies. He holds master degrees in physics and international management. Welcome, Philip.
Thank you, Nick. Good morning. I guess we all know the story now of the Serbian-American inventor, Nikola Tesla, who invented AC power generation and his fight against a certain gentleman called Thomas Edison, and how Tesla won. And that's why we have AC current coming out of our wall socket. And that's why we have an AC motor in our vacuum cleaner. And that's why we are literally bathed in AC magnetic fields. However, if you turn on a magnetometer, or as they're known these days, a Tesla meter, you'll find that it's really set up to measure DC magnetic fields. So that seems very unjust on a whole variety of levels. So we're going to try to make that good and make it up to Mr. Tesla today. We're going to talk about how you measure, how you visualize, how you analyze, and last but not least, how you map AC magnetic fields. We're also going to talk about some of the things we don't know how to do. And for this presentation, I'm using some examples. As most of us, I've been working at home for almost a year now, and I was looking around for a nice source of AC fields until I realized I had it sitting right in front of my nose. It's this desk lamp, and if you see the base there, is actually got a big toroidal transformer in it, and I will be measuring the AC field of that superimposed onto the DC field of the Earth using this sensor. This is not a Hall sensor, it's a flux gate sensor, which has the benefit of being very sensitive down into the nanotesla range. And the software that we're displaying all this stuff with is the software that comes with that sensor called EasyMag 3D. Now, I don't mention this anywhere else in my talk, so I might as well get it out of the way right here, is that as we will see, when you have an AC magnetic field, it's not just the magnitude that's oscillating, it's also the direction that oscillates. So if you're trying to measure these things with a single axis sensor of some variety, you're making life very, very difficult on yourself. Probably impossibly difficult. You probably won't get the right answer. So I'm assuming that we're using a 3-axis sensor, which is also the case here. Okay, so we want to measure a field. So what we have to do is adjust a couple of parameters. In our software, that looks like this. We have to adjust, first of all, the acquisition rate, because we want to acquire data fairly quickly. So I've adjusted my acquisition rate, as you can see, to 2000 hertz, 2000 samples per second. Now, that number was chosen with a certain method because this particular instrument has a bandwidth, measurement bandwidth of 1 kilohertz. So if I do 2000 samples per second, I'm sitting right at the Nyquist limit. In other words, I could sample faster, but I'm not getting any additional information. Certainly not information that you want, because after the 1 kilohertz, the anti-aliasing filter in this instrument starts rolling off, and so you're not getting good measurements beyond 1 kilohertz anyway. Then you have to think about averaging. Now, most instruments have some sort of possibility to do signal averaging to improve the noise performance. Generally, you want to turn that off. You can think of signal averaging as a big hammer. It sort of flattens everything out. And whereas what we're going to be doing is we're going to use a scalpel and sort of tease things apart using spectral methods. So turn off the averaging or set the averaging to 1. And then there's this final parameter called block size. Now that serves two purposes. One purpose is, since we're acquiring a fair bit of data, the transfer rate between the instrument and the computer gets to be a limiting factor. And blocking things together into big blocks and transferring a block at a time instead of one measurement at a time keeps the transfer from being a bottleneck. And the second use that we have for that is that we're going to be analyzing data. For example, we're going to take a Fourier transform to do the spectral analysis. And this is the size, the chunk of data that we will use to analyze. Okay, so it's got that dual purpose. Okay, so now let's acquire some data. And how do we visualize it? Well, one time-honored way is this scrolling plot. As you can see, you have multiple traces. You have the things that we measured, bx, by, bz, and you have two traces that we compute. One is the magnitude of the field, called B, that we all know. And then there's a computed trace called b.b prime that we'll talk about in a moment. And on this graph, you can see the DC offset of each one of these traces. You can see the AC amplitude of these traces. You can see the frequency. You can see the wave shape. So there's a lot of information on this plot. But it all sort of appeals to the left half of the brain. It's very analytical. So what if you want a little more touchy-feely sense of what's going on? Well, you can use this vector representation. And here's the same data represented on a vector plot to give you an idea of what's really happening. And now what you can see here is that we have actually the Earth's field vector that is just being modulated a little bit by the AC oscillation. Now we've slowed this down by what we call a time warp here of a factor of 100. So our 50 hertz, and it really is 50 hertz because I'm in Europe, our 50 hertz cycle time becomes a half hertz oscillation that you can see here. So these are two ways, good ways of being able to visualize the data, but often we want to be able to analyze the data. So now here there are basically two big classes of things in our toolkit. One is spectral analysis, and the other is computing various figures of merit. So let's talk about spectral analysis first. Okay, we're going to take a Fourier transform. That's clear. But a Fourier transform of what? If you take a Fourier transform of bx or a by or a bz, you're not getting the full story. On the other hand, if you take the Fourier transform of the vector magnitude b, you're making a big mistake. And that is illustrated in the diagram on the right here. What I'm showing here is a very pure sine wave with its Fourier transform comes out to a single peak at the frequency, which I've chosen to be 1. Now, if I compute the magnitude of that, well, it's always positive. So actually, it's going to do a full wave rectification. And as you can see, we now have a DC offset. That's that component right there, component 0. And the base frequency wiggles twice as fast as the original signal. So the lowest frequency component is actually at 2 instead of 1. And then we have some overtones because this is not a real sine wave. So you get a totally different spectrum if you analyze the sine wave or if you analyze the magnitude of the sine wave. So what we've done is we've invented this fake component called b.b prime. And what it is if you imagine that your vector is oscillating like this, so the direction of oscillation is computed to be this, and then you project the B vector onto that, and that reconstitutes the sine wave. So it's as if you had taken a single axis probe and you had aligned it parallel to the oscillation, and you were now measuring that and doing the FFT of that. And to show you what that looks like in real life, here's the Fourier transform of our B dot B prime that we've calculated, and the same data if we compute the Fourier transform of B. Now, of course, life is a little messier in the real world than it was on my nice little diagram, but still you can see that these even harmonics really come up in the if you do this on the B. So you get a completely incorrect picture of what's going on if you take the Fourier transform of B. So B dot B prime, you may not have read about it in your textbook, but it definitely works and it definitely is useful. Now, instead of looking at a plot like this and saying, okay, on this log scale, the amplitude of this peak is about so much, you can do that automatically, and you can have it look at the frequencies for you. So here are the frequencies of the peaks that it's finding at 0, 50, 100, 150, 250. In other words, all the odd harmonics. And it'll give you the amplitude of that peak. And you can also set some sort of an exposure limit, which is shown here in green. And it'll complain to you when you exceed that exposure limit. So this is all stuff that can be done in real time these days. It's just quite nice. Okay, so that's spectral analysis. Now let's talk a little bit about the various figures of merit that you can calculate. So the idea here is, instead of looking at the frequency spectrum, I want to have some sort of a figure of merit that gives me an evaluation of the complete signal, the effective magnitude of the signal. And what people usually use is the RMS value. And so here, that includes both the DC component as well as the AC component. So here we see what happens when I take my sensor and I move it away from my AC field source. And as you can see, the field drops and it approaches a DC value, which in fact is roughly the Earth's magnetic field. Now, if you're only interested in the AC component, then there's another measure, which there's the peak-to-peak amplitude of that B dot B prime that we just calculated before. And as you can see, as I move him away from the source, he tends towards 0, right down here. Now, if you've ever used peak-to-peak measurements, you know that they're very sensitive to even a single outlier. He will completely change the value of the peak-to-peak amplitude. So it's an unstable measurement. So for better stability, you can compute the standard deviation, which is exactly what it says, the statistical calculation of the standard deviation. And it has the effect of taking into account all of the measurements in your sample, and therefore you get a good smoothing effect. And generally, with sinusoidal type oscillations, the standard deviation will be roughly 1/3 of the peak-to-peak value. You can also cut these the frequency band up. So here we've have the frequency band divided into 0 to 50, and 50 to 1 kilohertz. And we're calculating, in this case, the standard deviation of all the different components. And once again, you can, once again, you can set an exposure limit where it will complain if, for example, the standard deviation exceeds a certain limit. Okay, now getting to the fun stuff. How do you map an AC magnetic field? Well, basically, you need multiple sensors in multiple locations. You need an array of sensors. So the sort of robot-driven mappers, such as a Senis mapper, is really not appropriate for this job. You can do play some games and do synchronization, but it's really not the right tool for the job. The other mapper that's on the market that is fairly well known is the MagCam mapper. Now this is getting closer to what you need. It's an array of sensors, but it's a very, very closely spaced array. So the area is much smaller than here. As you can see, the area of this mapper is 80 by 80 millimeters. Sorry, just messing these things up again. The main difference is that whereas this array has real 3-axis sensors, in the MagCam, it's actually computed. The 2 of the axes are computed. So that is a significant factor, especially for these AC fields. Now, this particular system was developed and built by the Fraunhofer Institute in Germany. Metrolab will be distributing it. You can see the specifications here, 32 by 32 array on an area of 80 by 80 millimeters. And all you basically do is you just plop the magnets on there, and in real time, you will see the map appear. So what I did is I went into the lab this time to get a real coil, and I just plunked it on there and powered it, and in real time you get this map. And this is really, really beautiful. It's as if I had computed it. And just to make sure that, or try to convince you that I didn't calculate this, I moved the coil off into the corner. So now you see the oscillation is off in the corner someplace. And there's 1,001 different ways of displaying this data. I decided to display just the Z component. And if you're wondering what the BX and the BY components are doing, they're just planes that rock this way and this way. But you could also display this as porcupine plots or any number of different plots. Okay, so as you can see, we can do lots of good things. Now I wanted to talk about a few of the things that we don't know about yet. The first problem is a problem, but it's actually been solved. Okay, but I thought I'd present the solution anyway. If you want to calculate this RMS value, and for example, this document here, this European Union directive that specifies limits for exposure to electromagnetic radiation, it refers to our RMS values, but nowhere does it tell you how you calculate these RMS values. And what do you mean RMS of the magnetic field? The magnetic field is a vector, and I don't know how to calculate the RMS value of a vector. I mean, I know certain, or I can imagine certain special cases. So for example, if I have a DC field, okay, I can say the RMS value of that is just the field magnitude. Or if I have a pure AC field, like a sine wave, okay, I can say that is the RMS value of that sine wave. But what if I have a combination of that and an oscillation on top of that? What do? I add the two components? What? Well, the illumination comes, if you think back to where we ran into RMS to begin with. And it usually came with this power formula, power dissipated by a resistor R with a current I in it is P equals I squared R. We all learned that at our grandparents' knees. But if you have an AC current, then the average power depends on the RMS value of the current. So the question is there a comparable formula in the world of magnetism? And it turns out there is. It's called the energy density of a magnetic field, has this form, B squared over 2 mu. So it depends on B squared, just like the power depends on I squared. So it's not too much of a leap of faith to say, okay, let's say the RMS value of B, what we mean by that is that if you have an AC field, this will give you the average energy density of the magnetic field. Now that doesn't tell us how to compute the thing yet, but it does tell us what it does for a living. Okay, but if this is true, then I can separate my magnetic field into its 3 components and say that the total energy density is equal to the energy density of the X component plus the energy density of the Y component plus the energy density of the Z component. And each of those components, I don't have any problem calculating the RMS of those because there's only one thing wiggling. So if you write all that down and turn the crank, as I've done here, you find that the RMS value of the vector B is actually just the RMS value of the magnitude B. So this is a wonderfully simple result, which is probably obvious to you, but it wasn't obvious to me. And it's interesting to note that, okay, this is true for RMS, but if you want the other figures of merit that we were talking about, for example, the standard deviation or the peak-to-peak amplitude, those things, you're better off using that B dot B prime we invented because of this halfway or full wave rectification. Now, talking of the B dot B prime, that brings us to our next problem. How good is this thing, really? Well, the answer is it's perfect, as long as the field satisfies the assumptions that you made about it. And the assumption that we made about it is that it oscillates in a linear fashion. And that is a good assumption in a number of cases. So for example, if you take a solenoid, down the middle of the solenoid, the field will oscillate linearly. And if you take a wire with an AC current in it, the field will go around it like this, back and forth. So if you stick a probe right there, you'll see a field oscillating back and forth. Those are linear. And in general, if you get far enough away from your magnetic system, your AC magnetic system, all you will see is the current flowing in and out, and it basically looks like a wire, and you get back down to this oscillating linear oscillation. However, if you get into the near field, it doesn't necessarily have to be linear at all. So here is an example again of my AC transformer lamp transformer. But now I've moved the sensor to be very close. And as you can see, it's no longer linear at all. As a matter of fact, what's it look like? It looks like a hula dancer. And B dot B prime does not work for hula dancers, guaranteed. As a matter of fact, if you have a perfect hula dancer where it's going around in a circle, B dot B prime will be 0. So we know that's not right. Okay, so what we're looking for is a generalized way of extracting periodic signals in multidimensional data. And as I was preparing this talk, as a matter of fact, I found a literature reference that does pretty much that. And so I think the math is applicable. I think in the future, we will be able to solve this problem, but it's not there yet. Okay, so these are analysis kinds of problems. What about real instrument problems? Well, I got one for you. When you look at your specifications of your magnetometer, it gives you 2 figures of merit. It gives you a range of field values that you can measure. And I've plotted these on the vertical axis here. And it gives you a range of frequencies that the system, so the bandwidth, the measurement bandwidth of the system. And the implication is that you can use any combination of those two. It's not true, not true at all. Well, you can, but you don't necessarily know what you're measuring, because as soon as you get up here into this red zone, it's no longer calibrated. So you don't know what you're getting, and what's worse, we don't know what we're giving you as instrument manufacturers. As you can see, we can calibrate along the DC axis pretty well. I think Metrolab is the champion there. We regularly calibrate up to 14 Tesla. And you can measure up to a certain frequency limit, and I believe Magnetphysik is the champion there. They have equipment to calibrate out to 5 kilohertz. But as you can see, only up to the millitesla range. As you can see, the field strength I plotted on a log scale, just so that I wouldn't end up with just a green line along the bottom axis. So there's actually a huge area that we cannot calibrate. And this isn't just academic. I think any self-respecting motor, if you were to measure the field between the stator and the rotor, would probably fall into the red range. And certainly a magnetizing fixture would be way out into the red range. So I think this is something that we as instrument manufacturers need to solve, to address for the benefit of our clients. Okay, so bottom line is, there's lots of things that we can do today that we couldn't do yesterday, and hopefully there will be things that we can do tomorrow that we can't yet do today. It's an evolving field, and stay tuned. So if there's any questions, I have, according to my count, almost 3 minutes. I don't see any popping up on my panel right here, but if you have any, please feel free to share them with me. Otherwise, as Nick mentioned, I'll be in the networking lounge afterwards. Thank you very much.